Thank you, Chairman. I'm Weda Koya, the first year student of master course of the University of Tokyo. Today, I'd like to present our study, Prediction Model for Fatigue Life Concerning Microstructures of Steel. These are the contents of today's presentation. First, background. Fatigue is damage from repeated return force. Many serious damage are related with fatigue. Fatigue can also be a bottleneck in application of advanced materials. So, to predict fatigue life is important. Fatigue life is expressed in SN curves. This is a relationship between stress amplitude and fatigue life. It is known that there is a scatter in fatigue life. This cause is said to be a microstructures, uneven construction, or change of stress. So the relationship between fatigue life and microstructures need to be clear. Objective of this study is the development of the fatigue life prediction model concerning quantitative effect of microstructures in ferrite parallel steel. Ferrite parallel steel is most popular steel for practical use. Next, observation of fatigue graph initiation and propagation. In fatigue test, we use this test steel. In fatigue test, this specimen is used. This specimen has a notch in the center, and the place where crack can initiate is limited by this notch. Test condition is on this table. We observed a specific number of loss cycles. By comparing picture of same place, we can see how crack propagate. This is crack behavior. By turning back these pictures, we can see the crack initiation site. Crack initiate when the number of loss cycles 4,000 times. By comparing picture of this and picture after etching, we can see the crack initiate in flat grain. Next, the development of model to predict fatigue life. This study based on a theory, a model for propagation of small fatigue graph interacting with grain boundary. This theory needs 4 input parameters to calculate fatigue graph. CTOD value is calculated from this formulation, and crack propagation velocity is calculated from this formulation. However, this model is for one-dimensional, and there is a problem on quantitative prediction precision. So we did an extension to 3 dimension. This study models surface model specimen as 2D surface by 2D inner of specimen. In modeling of ferrite parallel grain, this model regards ferrite grain as a circle and parallel grain as an ellipse based on a preceding study. This is the outline of this model. First, where crack can initiate is defined as an active zone. Next, active zone is divided into area elements. Area elements are filled with grains on Monte Carlo method, and grains are given crystal orientation randomly. Crack initiation is estimated from stress distribution from FEM and crystal orientation of each grain. After crack initiation, this model considers crack propagation. First, grains are filled on Monte Carlo method. Next, these grains are transformed into grain loads. By this process, this model can regard two-dimensional arrangement of grain as one-dimensional. Next, this model calculates CTODs and calculates fatigue life. Calculation for all grains are conducted, and the minimum is the fatigue life. Next, I'll talk about this grain arrangement in more detail. First, grains are next to the crack initiation grain. Grain is transformed into a sector which has the same area, and central angle is calculated. Next, grain is transformed into semicircle. Next, grain is arranged next to the semicircle. This process is repeated until all grains are arranged. So each time the total of central angles exceeds pi, these grains are averaged into one grain row. Next, validation of the model. In fatigue test, we used these test fields. For model variation, we conducted fatigue test in this condition. This is the result of fatigue test. The steel which has a smaller grain has longer fatigue life. The friction stress in this model is defined as yield stress of infinite-sized single crystal. Hall-Petch relation and ratio of hardness is used to calculate this friction stress. The result of calculation is on this table. FEM and finite element analysis is conducted to obtain stress distribution for modification. In FEM, cyclic stress-strain relationship is used. The parameter of propagation velocity is calculated by model calculation of test field B. This is the value of C and N. Using this C and N value, we conducted model calculation of test field A and C. Both predictions agree with experimental result in a high accuracy. Last, this is the conclusion. Thank you for listening.